Okay, so we're back. We're moving into section 7.2 now that financial mathematics is over, and this is talking about sets. So there are three parts to this section. Right. So the first part will be definitions and notations, and that will cover basically problems 1 through 24 in section 7.2. Introduction to Venn diagrams, so intro to Venn, which you probably have seen before, but we'll use them to count. And that's problems 25 through 36. And then third part is constructing a Venn diagram. Venn was a mathematician in the late 1800s. Who sort of invented these sorts of things. So that's the three parts of this talk. Problems 1 through 24 about definitions and notation, 25 through 36. These all are dealing with one Venn diagram, right? So it looks like a lot of problems, like 12 problems or something, but it's really just a bunch of questions about one thing. 67 through 78 also are just a bunch of questions about one thing, right? So it's not really, 12 separate problems. Okay, so we'll start with definitions and notations about sets. What is a set? Well, it's a collection or list of stuff, which isn't actually all that useful, but it is, the definition doesn't seem all that useful, but it is actually a surprisingly nice thing. So it's a collection or list of things, right? So students at SCSU, for example, is a set, right? Because some people are students at SCSU and some people aren't. Even numbers is a set, 2, 4, 6, 8. Some numbers are even, some aren't. Planets are a set because some things are planets and some things aren't. Okay, so notation. The usual notation for a set is listing notation. So 1, 2, 3, 4, right? The braces, that means a set, right? And we usually give it a name. So A is the set that consists of the things 1, 2, 3, 4. So there's the set A. It's a thing with 4 elements. Or B, right? Sets don't have to be numbers. As a math class, we often have sets of numbers, but we can have sets of desserts. So ice cream, pie, and chocolate. Right? So B is a set, right? The braces mean a set of 3 things: ice cream, pie, and chocolate. So you just list the things that your set consists of. Okay, now let's call that 1 in our problems about notations and stuff. 2, the phrase X is an element of A, or in symbols X. Well, it looks like an E. This is actually the Greek letter epsilon. When we say X and you read is in, so when you see this, it says X is in A. So what does that mean? Well, if we look at the set A up here, right? Well, what are the things in the list? Well, 2 is in A, right? 3 is in A, right? It just means that this thing shows up in the list for A. 3 shows up in the list for A. But 5 is not in A, right? Because 5 doesn't show in that list. Pi is also not in A because it doesn't show up in the list. So this E means that it's in, or it's an element of the set, right? 3 is in the set, 5 is not in the set. And when in math, not in means just put a big slash through it. Okay, so that's a second notation. 3 is, well, I've used A and B, so we'll use X and Y for sets in general. X is a subset of Y. What does that mean? We'll put quotes around for that. Or X, and then we have this symbol. It's a sideways U, sort of, with a little half of an equal sign underneath. X is a subset of Y. Right? So this is read like that. So X is a subset of Y. So what does that mean? Well, X is a set, Y is a set. So suppose we have a set, we'll call it U. Let's see, where's my notes? We'll call it D. So we'll set up another set, that's D, and that just consists of these two things. And we can set up another set, E, that consists of, oops, not that, and a third set, F, that consists of, and the questions are, is D a subset of A? Is E a subset of A? Is F a subset of A? What does it mean to be a subset? So, D is a subset of A, or, well, D is the set 1, 2. Oops. And that is the subset of the set A, which is the set 1, 2, 3, 4. What makes something a subset? Everything in D is an A. Oops. Right? So D is a subset of A. 1 occurs in the list for D, but it also occurs in the list for A. 2 occurs in the list for D, but also occurs in the list of A. So if this list is somewhere in this list, then this is a subset of that. Is E a subset of A? Well, no. E is not a subset of A. Right? Because E is the set 5, 7, 9. A is the set 1, 2, 3, 4. Not a subset, because 5 is not in that, 7 is not in that, 9 is not in that. Right? So 5, which is in E, an element of E, because it's inside the list for E, is not anywhere in the list for A. So right? E can't be a subset of A. 7 is not in this list, 9 is not in the list. Now if we look at F, F is the set 1, 2, 5. Right? And I'll leave this little middle space blank because we don't know yet. Is F a subset of A or not? Right? So here's our list for A, 1, 2, 3, 4. Here's our list for F. 1 is in F, and it's also in A, so that's good. 2 is in F, but is also in A, so that's good. 5, 5 is in F, but it's not in A. So is everything in the list for F also in the list for A? No, 5 is not. So F is not a subset of A. Every single thing in the smaller set has to appear somewhere in the list for the bigger set for it to be a subset. If even one element is missing, right, like 5, then this can't be a subset of this because this doesn't have 5 in it. Okay, so those are the basic problems. Element of X element A subset B, those are sort of the basic concepts of sets, and this idea of a set as a list of things. And so problems 1 through 8 in section 7.2 are dealing with these 3 concepts. So you should be able to, pause the video now and go and look at those problems and see if you can do those, if you understand what element of, subset of, and list of objects is. Okay, so now we're going to move on to intersection and subset. No, sorry, not intersection, subset. Intersection, union, and complement. and this is dealing with problems 9 through 16 and 23 and 24. So after we talk about this section, then you should be able to do these problems. So intersection is this upside down U, intersection B. You can read that as A intersection B or the intersection of A and B, depending on how proper you want your grammar to be. What is A intersection B? Everything that's in both A and B, right? So both A and B at the same time. So let's start with a couple of new sets. We'll say A equals the set 1, 2, well, we'll keep A the same, 1, 2, 3, 4, and B equals the set 1, 3, 5, 7. So there's two sets, A and B. What is A intersection B? Well, it's everything that's in both of them. So 1 is in both, right? And we write a little curly bracket to indicate that we're dealing with a set. 1 is in both, so 1 is in our set. 2 is in A, but it's not in B, so that's not in both. 3 is in both, A and B. 4 is in A, but not in B. 5 is in B, but not in A. 7 is in B, but not in A. So it's just the numbers 1 and 3. Those are the only numbers that show up in both lists. And so that's the intersection of the two. A union B, right? And so we can read that as A union B, right? And so this symbol in between looks like a U, so it's a little bit easier to remember, right? If it looks like a U, it's a union. If it doesn't look like a U, if it's upside down, it's an intersection. What is this? This is everything that's in either A or B. So here for union, it doesn't have to be in both of them at the same time, it just has to be in either one. So if we take A and B as these two sets up here, here's A, here's B, what's in each one? Well, not what's in each one, but just list everything that's in either one. So 1 is in A, 2 is in A, 3 is in A and B, 1 is also in A and B, 4 is in A, 5 is in A, 5 is in B, 7 is in B. So there's our set. And when we write a union, write everything just once. Right? The number 1 is in A and B, but we're just listing everything that happens to be in either one of them. So 1 is in A, so just write it down once since it's in both. 2 is in A, 3 appears in both, but we don't need to write down 3 and 3 twice, so we just write down 3 once, 4, 5, 7. So A union B, you just write down everything that's in both. Now, so that's union and intersection. Third part is complement. So if A is a subset of U, then A prime or A complement. So complement is denoted by having a little prime up there. It's with an E, not with a I. Complement is, well, that's everything that's in A in U that's not in A. So the complement, right? The complement to a set is everything that fills out the larger set that it's a subset of. So we'll keep A as 1, 2, 3, 4. We'll keep B as 1, 3, 5, 7. And we'll set U to be the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's all the numbers from 1 to 10. So what's A complement? It's everything in this set U, right? So let's note here before we go any further. Note, A is a subset of U, B is a subset of U. Everything in A, right? 1, 1, 2, 2, 3, 3, 4, 4. Everything that's in A is in U, so A is a subset of U. Everything that's in B, 1, 3, 5, and 7, is in U, so B is also a subset of U. Okay, so what's A complement? Well, it's everything that's in U that's not in A. So 1, 2, 3, 4, 5. 5 is in U, but it's not in A, so 6, 7, 8, 9, and 10. So A prime is that set. What's B prime? Well, 1, 3, 5, 7, that's in B. So 1 is in U, but it's also in B. 2 is in U, but it's not in B. So that's in B prime. 3 is in B. 4 is in U, but not in B. 5 is in B. 6 is in U, not in B. 7 is in B. 8, 9, 10. Right? So A prime and A together make up all of U. So A prime is everything that's you need to finish out U that's not in A. And B prime likewise is everything that's in the set U that's not in B. We need the set U because you know, A subset U, because otherwise complements are too big. If you just said A prime, what's everything that's not in A? Well, you know, I'm not in A, right? Because I am not the number 1, 2, 3, or 4. You're not in A because you're not the number 1, 2, 3, or 4. Cheese is not in A because cheese is not the numbers 1, 2, 3, 4. And so, you know, everything that's not in A is an awful long list. What we're really interested in is if we have a smaller list, right? If we're just interested in the numbers, say, from 1 to 10, then we can look at A and say, well, okay, A complement is the numbers 5, 6, 7, 8, 9, 10. So you need to, whenever you're talking about a complement, it has to be the rest of a bigger set that contains A. And that should get us through problems 9 through 16 and 23 through 24, except for one last bit, the empty set. So, what is A intersection A prime? Right, so here's A prime, here's A. What's in both of them at the same time? Well, 1 is an A, but it's not an A prime. 2 is an A, but it's not an A prime. 3 is an A, but it's not an A prime. 4 is an A, it's not an A prime. There is nothing. And so to be able to express that, we have a particular symbol, the Greek letter phi. It's just a 0 with a dash for it, with a dash through it. And this is called the empty set. It's the set that has nothing in it. It's a list of nothing, of no elements, right? So if you tried to define the set of people who are 100 feet tall, that would also be the empty set because there's nobody in it. This is a useful fact about complements, right? Complements and their sets are always, their intersection is always empty. If the intersection between two sets has nothing in it, we call them disjoint. D-I-S-J-O-I-N-T. Right? There's nothing in both of them. Okay, and so now we should be able to do, you should be able to go and do problems 9 through 16 and 23 through 24. Okay. And then the very last thing before we get on to Venn diagrams is another style of set notation called set builder notation. And I've mentioned it briefly in the previous ones. This is dealing with problems 17 through 22. So we'll set A to be the set, well, it'll be written like this. So what the heck is all this? Right, A is the name of the set, and equals just saying it's this thing. Again, braces tell me that this is a set. So if I want to read this whole thing from left to right, it's the set, that's what the braces mean. X, that's a variable, so of all things, the vertical line is usually read so that. So the set of all things so that x to the fourth, so that the thing to the fourth power equals 16. Right? So the set of all things so that whatever thing that is, you raise it to the fourth power, you get 16. And that's actually not hard to solve, right? We can actually figure out what the solutions to those are. There's only two solutions. It's -2 and 2. So it's a way of writing down this set, which is a list of two numbers, -2 and 2, by referring to a property that they both share. So this is a property of those numbers. And so you can refer to things as by their properties. So we can define a set B equals set of all x so that x is a professor of 196 fall 2013. Right? So right, B is the set of all things so that whatever that thing is, they're teaching Math 196 in fall of 2013. And so this is me and Professor Johnson, who's teaching the other sections of 196 this fall. Okay. So this is a property that we both share. We're professors of 196, fall 2013. So you can write things by talking about their properties or by listing them. So what's C equals the set of all x so that x is a 100-foot tall human. Right? So the set of all things that are 100-foot tall humans, and C is the empty set because there's no 100-foot tall humans. And again, problems 17 through 22 are just taking set builder notation and asking for what the listing property is. So you should be able to go and do those problems now. Okay, and now we'll move into Venn diagrams. So this is the second part. Venn diagrams are a useful way to to visualize some of these notations that we've been talking about. So what's a Venn diagram? Well, there are lots of them, but this is sort of the most basic one. Two circles inside of a box. We usually take the left circle to be the circle A and the right circle to be the circle B, and then the whole box is what's called the universal set U. Great. So there's our Venn diagram. And so we can start asking ourselves, well, what do these various combinations of things that we were just talking about look like in a Venn diagram? So we'll just redraw that and we'll say, okay, here's my Venn diagram. There's A, there's B, the box is U. What is A intersection B? Well, remember that A intersection B is everything that's in A and in B. A is everything inside this circle. B is everything inside this circle. So what's inside both circles? So A intersection B, that's this region. That's everything that's inside both circles. Okay. So we can start picking out regions. What's A union B? Right? This is A, this is B, this is U, the universal set. A union B, well, that's everything that's inside of the circle A and also everything that's inside of the circle B. So that has to be this whole region inside the two circles. What's another example? What's A prime? What's the complement of A? So here's our set U. A is a subset of U. There's A. There's B. A prime, right? That set is everything that is inside of U, everything that's inside the box, but not in A. Everything that's outside of the circle, but inside of the box. So that's all of this stuff. Great. And that includes a bunch of B, right? Because a part of B is outside of the circle for A. So that's A prime. You know, and it can get a little complicated, right? What is A prime intersection B, for example? Well, we know what A prime is. It's everything outside of A. That's all this stuff. What's B? B is everything that's inside this circle. So what's A prime intersection B? Well, it's everything that's outside of A but inside of B. It's just this part. So A prime intersection B is everything that's outside of A but not in B. And we can draw more circles. We call this A. We call this B. We call the whole set U. Don't forget my labels over here. A, B, U. What's A union B complement? Well, A union B is everything that's in either A or in B, right? So that's everything that's inside of these two circles. A union B complement, that would be everything that's inside the box that's not in the two circles, right? So that has to be everything that's outside of the two circles. Okay, so if you know the notation and you've got the diagram, you can figure out, you know, given a particular notation, which region of the box you're talking about. So problems 20, what were those? 26 through 30, 25 through 36 are dealing with a Venn diagram that's got numbers in it. So here's U, here's A, here's B, and suppose we have a Venn diagram that's got the numbers 7, 8, 22, and 43. What do these numbers mean? Well, there's 7 things in this part of the box. There's 8 things in this part of the box. There's 22 in this part of the box, and 43 overall. So, how many things are in A? Well, 15, right? Because the circle A consists of 2 parts, this part and this part. So 8 plus 7 is 15. How many things are in B? Well, 22 plus 8. 30 things are in B. Right? Because B consists of 2 parts. How many things are in A intersection B? Well, that's everything that's in this part, because A intersection B is the overlap between the two. So just 8. How many things are in A union B? Well, A union B is this part plus this part plus this part. So it's going to be 37. 22 plus 8 plus 7. Note an important point here. Don't double count the 8. Right? And what's that mean? Well, how many things are in A? 15. How many things are in B? 30. How many things are in A and B combined? It's not 45, because we don't want to count this twice. So A is 8 plus 7, B is 8 plus 22, but A union B, that's 7 plus 8 plus 22, don't count that twice. So it's not just the stuff in A plus the stuff in B, it's the stuff in A and B, but don't double count the intersection. And we'll talk about that some more. So later in 7.3, I guess. How many things are in A prime intersection B? And if you remember up here, that's just in this part. And so A prime intersection B is everything that's outside of A, so not these 2 parts, but inside of B, so just that, 22. So how many things are in U? Well, that's 7 plus 8 plus 22 plus 43. We already know 7 plus 8 plus 22 is 37, so that's 37 plus 43 is 80. So we have 80 things total. 7 of them are in A, but not in B. 8 of them are in A and B at the same time, 22 are in A but not in B, and 43 are neither in A nor B. And so if you go through problems, what was this, 25 through 36, right? They just give you a chart like this, and they ask you these sorts of questions, how many things are in various things, and you just identify which region they're talking about, and then you can answer the question. And the last part is dealing with problems 67 to 78. This is very much like the part we just did, right? Except you have to set up the Venn diagram first. So here's a similar example to 67 through 78. They're all dealing with the same Venn diagram. A survey of drivers found that it's not just a survey of drivers, it's a survey of 1,000 drivers, found that 680 stop at Dunkin' Donuts when they're on a road trip, and 420 stop at Krispy Kreme, because we all know that good road trips are fueled by donuts, and 150 did both. So set up a Venn diagram. So we'll set up, here's our Venn diagram. U, that's our universal set, that's our collection of all drivers. We'll call this one D. Those are the ones who stopped at Dunkin' Donuts. And we'll call this one K. Those are the ones who stopped at Krispy Kreme. Okay, so what does the data tell us? Well, there's 1,000 drivers total in the box, or in the Venn diagram, and we need to break them up so we know how many are here, how many here, how many here, and how many here. 150 did both. What does that mean? They're in D because they stopped at Dunkin' Donuts, and they're in K because they stopped at Krispy Kreme. And so that's D intersection K. So we know there's 150 there. Now, 680 stopped at Dunkin' Donuts. So that means there's 680 total drivers in D. But we know 150 are in D intersection K. So D is this whole circle, so this region and this region. We know there's 150 there, and we know there's 680 total. So 530 are in D, but not in K. Right? And in D, but not in K, well, not in K is K prime. In D is D, so D intersection K prime. So that's 530 go here. We also know that there's 420 stopped at Krispy Kreme. So there's 420 in K, but 150 in both D and K. Right? So Krispy Kreme drivers are everybody in this circle. 150 of them stop at both Krispy Kreme and Dunkin' Donuts, but 420 stopped at Krispy Kreme total. So how many are there? 270. Right, so there's 270 drivers stopped at Krispy Kreme, but not at Dunkin' Donuts. So that's D prime intersection K. Not in Dunkin' Donuts and in Krispy Kremes. The last thing we need to know is how many people are out here. These are people who didn't stop at Dunkin' Donuts and they didn't stop at Krispy Kreme. So how many people stopped either at Dunkin' Donuts or at Krispy Kreme? So this is to find out how many are in D union K. So an OR means union. Well, 530 plus 150 plus 270. And that's 950 drivers. So 950 drivers stopped either at Dunkin' Donuts or at Krispy Kreme. They surveyed 1,000. How many stopped at either one? That's D union K is 950. How many people stopped at neither then? Well, that must be 50 people. And that fills out our Venn diagram. 150 people stopped at both, 530 stopped at Dunkin' Donuts but not at Krispy Kreme, 270 stopped at Krispy Kreme but not at Dunkin' Donuts, 50 people stopped at neither. So once you have this diagram, you can start answering sort of questions, right? You know, they have these questions like, what's the set of drivers who did not stop at either Dunkin' Donuts or Krispy Kreme? That's these 50 people. What's the set of drivers who stopped at Krispy Kreme but not at Dunkin' Donuts? That's this 270. What's the set of drivers who stopped at Dunkin' but not at Krispy Kreme? That's this 570. And so problems 67 through 78 ask you to set up this diagram, figure out which numbers go in which, and then 67 through 78 are just answering these questions about which region, what's the number that's in each region. So that's section 7.2. At this point, you should be able to answer all the questions in the book. And remember that the book questions are the questions that are going to be on tests and quizzes, along with the worksheet problems and the Math Excel problems.